Okay, like I said, my name is Paulo Reis. I come from the University of Coimbra, Portugal, and this work that is entitled Self-Eating Effect on Hybrid Composites is a collaborative work with our colleagues from Poland, Andrzej Katunin and Dominik Wachla. Okay. The motivation for this work is related with the polymer composites have enormous engineering applications due to their strength-to-weight ratio, low cost, and easy manufacture. Everybody knows, everybody feels the pressure for environmental and sustainable materials. And in this case, hybrid composites involving natural fibers can combine strength, cost-effectiveness, environmental sustainability, and the ability to optimize design and performance in practical applications. In this case, we can say that this topic is becoming nowadays much more increasing and pertinent and should the focus of several studies for future industrial application. Okay, by other words, it is estimated, and everybody knows and feels that fatigue is the cause of 90% of all mechanical service failures. In this context, is very dangerous and is necessary to study for all type of materials. However, the majority of the studies focus on fatigue behavior is assessed based on the classic SCN curves approach. However, new strategies are needed for faster and efficient assessment. In this case, this study focused on analyzing the critical self-eating temperature as indicator of the fatigue limit for application in hybrid composites. Okay. The material that we used in this study was based in bidirectional fabrics containing different fibers like carbon, glass, Kevlar, and flex fibers, which were combined with a green epoxy resin, a Sicomin SCR green epoxy 56 resin. This resin has the particularity to have 60% of products from the vegetable origin. Now we can say that is a green resin, like the name reflects. Okay, the configuration that was studied can be saw here and is laminated, composed by 3 layers of flex, hybrid laminates combining carbon, flex, carbon, Kevlar, flex, Kevlar, and glass, flex, glass fibers. The system used to produce the fatigue load is shown here, and we can observe an equipment where is based in a shaker, number 1, the equipment number 1, and that produce the oscillation, and the specimen is the number 5. Okay, this shaker produced the loading in control displacement, and you can capture by thermography the map of temperature in the sample, and you can obtain also the displacement and consequently the load, the force of that is applied to the sample. Simultaneously, we apply also acoustic emission system in order to analyze the acoustic emission produced during the fatigue tests on sample. Okay, about the results. Okay, here the strategy, nothing is new. We have here the typical response of the material to the applied load where you can observe that the temperature increase based on three regimes. Phase 1, Phase 2, and Phase 3, which is characterized by an initial increase, higher increase of the temperature. After that, there are stabilization and again a strong influence of the temperature with a respective increase of the temperature and final collapse. This is very well reported in the literature, and we can see the diagram. Okay, what we want to do, we want to find the critical point related to the critical self-heating temperature. Okay, is here in this point. And to obtain this point, because what we know is the number of cycles to failure is the final point, what we want to know is how much is this temperature. And this evolution can be governed by the equation 1. The equation 1 related number of cycles, specimen temperature for a specific number of cycles, and the increase of the temperature and the specimen heating speed. And manipulating all these variables and using this equation, we can observe we can find the critical temperature, self-heating temperature here in this point. All this methodology is very well described in this paper, and this curve we can see that these for a fixed number of cycles, we can observe the effect of the load on the sample. Based on this theoretical approach that is not new, we can obtain here the curve. This is a typical curve for a load, a specific load. We can see here the curve that is composed by the three stage that was reported before. And we have here the critical self-heating temperature. What is this temperature? Is the temperature when this line are deconnecting with the red line. This is the initial three stage. Okay, in this graph, we can observe better the critical self-heating temperature. Okay, when we find this value, the critical self-heating temperature, we can put in a graph in this plot temperature versus load, or we can convert to stress, and we can have these points, and we can adjust two lines, two curves, and this point is the fatigue limit. Okay, in this case, we can obtain the stress or load for fatigue limit. Based on this, what we want is find the critical self-heating temperature. We don't want to analyze in terms of stress or load. We want to analyze in terms of temperature. And in this case, for all tests, we have this point that is converted in this table. Okay, here we can observe that the critical self-heating temperature depends on the material. For example, only for flax, the temperature is around 51 degrees. But when we analyze in terms of hybrids, the temperature decreases, and it depends on the materials that are involved. For example, for carbon flax, we have 42 degrees, around 42.4 degrees. For Kevlar and flax fibers, we have 36.45 degrees. And for glass combined with flax fibers, we have 45.3. Okay, This is not new, but confirms that this strategy can be applied to the hybrid laminates, and we can observe also that there are influence of the constituents. In this case, we maintain constant sorry, the resin, but we change and combine different fibers. And here we can observe the influence of the fibers in this case. Okay, but this is necessary to confirm these values. And we use it other methodology that is very well understand and explain, disseminate in literature that is based on acoustic emission. What we have here is the acoustic emission response for a specific sample, and we can observe for this case that this is the accumulation of the noise, and we can observe that for a specific value of time, the increasing is too much. This means that there are too much in competition. This means that could be this value the fatigue limit, or can be related with the self-heating temperature. Okay, in this case, this is the graphic that we obtained in the previous, in the right position. We have the graphic that was obtained temperature versus time in the previous results obtained by the thermography. And when we combine these two graphics, we can observe here that the results coincide very well each other. We obtain two lines, that is the self-heating temperature critical value, and these lines are very well superimposed by the strategy obtained by the thermography and strategy used by acoustic emission. In this case, we can observe that we have good results that are proven in these tables. These tables was based in the self-heating temperature and here by the acoustic emission. And we can observe, for example, for flex, that the value was 50.8, and for the acoustic emission is 50.9, but is inside of the standard deviation. With this, we can say that this strategy proves that the thermography is a very good indicator for the self-heating temperature, and we can estimate a critical self-heating temperature that we can prove this evidence by the acoustic emission. Okay, concluding, we can observe here that with increasing of the temperature, we are much more closer than the TG of the resin, and we have effects of the mechanical response of the materials. We can observe that the strength, the bending strengths decrease, and we can observe the bending modulus also decrease. In conclusion, we can say that the critical self-heating temperature can be used as an alternative indicator of fatigue limit, and has the initiation of structural degradation due to the fatigue loading, what was confirmed by temperature and the acoustic emission response. Critical values of the self-heating temperature exceeding the glass transition temperature of materials lead to significant degradation of the material. Okay, thank you very much by your attention, and any question, please.